Welcome to this new episode of Not So Fast. In this video, what we are going to look at is a very often claimed generalization of Newton's second law when there is a time-dependent mass for a given object. What we are going to see here is that this new generalization of Newton's second law is actually inconsistent with Newtonian mechanics, and as a result, we do not recommend its use in, for the most part, any problem at all. So now let's have a look at what this popular claim is about. Starting with Newton's second law, where you need to be in an inertial frame, and you've got that the mass times the time derivative of the velocity is equal to the force. Now, if m, which is the inertial mass of the system, is a constant, then you can put it in this following way inside the derivative. Now, this quantity mv is actually known as well as momentum, and momentum plays a very important role in mechanics. Now, the thing here is that because we can write d of mv over dt is equal to f, the Newton's second law has been summarized by the following slogan: force is equal to the rate of change of momentum. Now, if we trust this particular slogan, even if the mass depends on time, then this leaves us with the following result, which is that d of m of t times v over dt is equal to f. Now, because of the so-called product rule, when we take derivatives of a product of function, we get the following quantity. So you see that the equation of motion, which is not anymore the traditional Newton's second law, has an extra term on the very left, which is v times the rate of change of the mass of the system. First of all, let's note that if there is no external force acting on the system, then we are going to get the following equation. So on the left, you've got m dv over dt, so that's mass times acceleration, is equal to minus v dm over dt. So it's as if the right-hand side was a force that was due to the fact that the object is losing mass. So what we are going to see now that we are a purported generalization of Newton's second law, we are going to see what could be the implication of this particular equation. Now, this object is seen from an inertial frame with a velocity v, and as it is moving, what's going to happen is that there is a term which we have seen on the right-hand side of this generalization proposed for the second law of Newton, which is minus v dm over dt. Now, because the rate of change of mass is negative, right, because the object loses mass, then we get that times minus, it becomes a plus. So we are going to get a term which is like this, which means that we are going to have an accelerating force for the object. And therefore, it's going to move like this and accelerate forward. Now, let's have a look at the first objection to this particular scenario. First of all, this initial, let's say, appreciation that an object losing mass is going to accelerate was done from an inertial frame where the object was going at a velocity v. Let's say it was actually observed by Alice. Now, Alice wants to see as well what's going to happen if she matches the velocity of the object at a given moment. So for this, she increases her velocity, and as such, the relative velocity of the object becomes zero, okay, eventually. When it does become zero relative to Alice, Alice stops accelerating. Now, what she is going to observe is that because the velocity relative to her is zero, then the equation we've seen earlier is going to become zero as well. So you've got zero and then times anything is going to give rise to zero. So now we are in a situation where we've got two observers, or in fact that was the same but at two different times, if you will. In one case, an inertial observer, Alice, after she has matched the velocity of the object at a given time, and then in that case she's going to observe zero acceleration on the object. Now, on the other hand, you had the Alice from the past, who observed that there was, in fact, an acceleration, a forward acceleration, in fact, if initially there was a velocity for the actual object. But the problem here is that we've got two inertial observers who are witnessing two different acceleration states, and that's actually impossible according to Newton's first law of motion. A second objection that can be made spurs from the fact that the scenario we've seen where there is a forward acceleration caused by mass loss would hold irrespective of the mechanism for the actual mass loss. So for example, you could lose mass by simply ejecting material in the lateral direction, so perpendicular to the direction of motion. So in sum, you would have that by ejecting mass laterally, you could get a forward acceleration. The problem, though, is that this is in contradiction with Newton's second law of motion, which says that an acceleration is going to occur when there is a force in the same direction. With these two objections, we see that it's really difficult to maintain that this is a valid generalization or encompassing generalization of Newton's second law when the mass of an object is going to change with time. Instead, what needs to be done is to actually look carefully at the mechanism by which mass is being lost. In fact, there is a class of mechanisms that can give rise to this general equation that is being proposed, but then it's only true and valid for this specific case and only this case, not at all for any general time-varying mass. So let's have a look at how this works. To represent this, I've started with the object we were looking at, but now I fill this object with, let's say, detachable parts. And what we are going to do is basically set multiple stages to the mechanism. So first, you need to select a part to get rid of. And for example, this is going to be this one, highlighted in red. Once this is done, you then need to eject the part so that its velocity is 0. So the way it would work is that you would have some form of interaction, and then the main object will move forward while the detachable part is going to be left behind at 0 velocity. So let's see what we are left with. We have on the one hand a mass here, delta m, that has been removed from the main object, and this is going at v equals 0 in the initial inertial frame that people are looking at from. This main object is now going at some velocity which is a priori changed. So let's say v plus delta v, and delta v a priori could be, moving forward or backwards, we don't know yet. The remaining mass has been decreased by an amount delta m, so now it's m minus delta m. Now, what would be the force actually exerted on the particle delta m to go from the initial velocity v to the 0 velocity it is now at? So that's what we want to ask. Well, this is going to be delta m times 0 minus v, and then divided by some time delta t over which this interaction has occurred. So here you see delta m times 0 minus v is nothing but Newton's second law, where I take the variation of the velocity and then I multiply it by the mass, nothing else. So this can be summarized in the following formula, minus v times delta m over delta t. Now, what is the force exerted on the main body of the system? Well, Newton's third law of mechanics tells us that for a force that has been acting on the particle delta m, to put it to v equals 0, well, the same force equal in magnitude but then opposite in direction has been applied on the main body m minus delta m. And as a result, the force applied on the main body is plus v delta m over delta t. And as you see, this is the very same term as this forward accelerating force due to mass loss that we saw earlier. The difference here compared to the one we've seen before is that now this is in a context where this is in according to Newtonian mechanics principles. So where does that leave us? Well, we've seen with two objections that the alleged generalization of Newton's second law when it comes to variable mass systems is actually inconsistent with Newtonian mechanics. In fact, we've seen that it was incompatible with Newton's first law of motion, and it was incompatible as well with Newton's second law of motion. Now, we have also seen that if you know the detailed mechanism by which mass is being lost or gained, then it was possible to obtain, in a very specific case, the equation, this general equation that people are talking about. But you see the catch here. This equation, where d of m of t v over dt would be equal to some force or 0, this is only true in one very specific case. So this is quite far from a generalization indeed.